What is time? How do particles change over time? Hi, I'm Nima Amin, and this is the third episode of my Simplification Theory. In this series, I'm developing my own framework to implement a single particle, the Escentron, and build a whole world with it in a computer simulation. In the previous video, we saw that cosmic energy is the sum of kinetic and potential energies. We also said that potential energy itself is the sum of gravitational and levitational energy. In my theory, gravitational energy depends only on mass, and levitational energy depends only on pulse. In this video, I want to talk about the laws of motion. Motion is the change of position over time. For simulation, I treat time as discrete steps, delta t. Particles affect each other only inside the current delta t. So this delta t here somehow translates to the present time. The first thing we need to do is calculate the fields. The gravitational field at the center of a particle is the vector sum of the gravitational fields from all particles. The levitational field at the center of a particle is the vector sum of the levitational fields from all particles. I calculate them separately because their effects on particles are different. So let's go shopping. We need a mathematical base for our equations of motion. I pick Newton's second law and the universal gravitation. Here's the result. This is the gravitational law, and you can write it like this. And this is the Newton's second law. If we take out force and we merge them together, we get this. This means mass times acceleration equals mass times the field. The mass on the left side is the inertial mass, and the mass on the right side is the gravitational mass. In classical physics, inertial mass was considered equivalent to gravitational mass. As a result, acceleration was thought to be always equal to the field. But in the simplification theory, they are not equal. So I define a new factor, I call it the acceleration correction factor, and it is equal to the ratio of the remaining energy to the cosmic energy. As an example, the remained energy can be the remained gravitational energy. Imagine the Escentron as being made of two energy containers, red for mass and the blue for pulse. Both containers are connected to a drive engine, representing kinetic energy through a simple valve. A field can open or close this valve. So if a particle is placed in a gravitational field, the gravitational valve opens, and if it is placed in a levitational field, the levitational valve opens. The strength of the field controls the valve. No matter how strong the field is, if the remaining energy in the container runs out, it can no longer have any effect on the particle. Therefore, when the particle's remaining energy is depleted, it enters a state we call energy depletion. Even the strongest field has no effect on a depleted particle. We have two kinds of depletion, mass depletion and pulse depletion. In this model, acceleration is not always equal to the field itself. It is corrected by how cosmic energy is stored inside the particle. I define the gravitational acceleration correction factor as the ratio of gravitational energy to total cosmic energy. Let's look at a proton. Most of the proton's cosmic energy is stored as mass. This means its gravitational energy is dominant. So for a proton, the gravitational correction factor is close to 1. Now compare this with a photon. In this model, the photon has extremely small mass As a result, its gravitational energy is negligible. So the gravitational correction factor for a photon is close to zero. The key idea is simple. Acceleration depends on how cosmic energy is stored inside the particle. In the same framework, we can define a correction factor for levitational acceleration. The levitational correction factor is the ratio of levitational energy to total cosmic energy. In this model, the levitational energy is associated with pulse. Let's look at an electron. Most of the electron's cosmic energy is stored as pulse rather than mass. This means levitational energy dominates. So for an electron, the levitational correction factor is close to 1. Now consider a photon. In this model, the photon carries very little pulse. As a result, its levitational energy is also very small. So the levitational correction factor for a photon is close to 0. Once again, acceleration is not universal. It depends on how cosmic energy is distributed inside the particle. To close this video, I want to show you one of my favorite experiments. Two escentrons are released with the same initial energy separated by a distance. They accelerate toward each other, collide, and then bounce apart. Throughout this process, no energy should be lost. In the next video, you will see how electromagnetism can be constructed using escentrons. If you enjoyed these videos, please consider sharing them. This really helps me continue developing this theory and creating more content. And if you have any questions, feel free to leave a comment. I'll be happy to answer.